and it's going to be actually thinking about quantum gases, Bose-Einstein condensates, instead of quantum fluids for a while. Okay. So can we be a little quiet?
So I would like to thank the organizers for the opportunity to present this work here. So I'll be talking about quantum gases, Bose-Einstein condensates. I'll start by introducing what the system is. Actually, just reminding you that it's going to be trapped ultra-cold atomic gases. And I'll actually be dealing with finite temperatures. So I'll be asking questions about vortex dynamics at finite temperatures. And the talk has two parts. I'm not sure if I'll get through to the very end, but it's basically going to talk about vortex decay in the presence of an incoherent thermal cloud in these systems. And I'll do this by introducing some generalized kinetic model that goes beyond this Gross-Pitevsky equation and touch upon the issue of mutual friction. And then I'll go on to introduce what happens when you actually have fluctuations into the system. And for that, we need a stochastic description similar to those, for example, in high energy physics for studying kink formation. And there's some interesting analogies that I'll just barely touch upon towards the end. So the system, as you've heard, you've already seen this picture before, is basically a trapped gas of atoms. These are weakly interacting under the conditions we look at it. We're talking at temperatures of the order of hundreds of nanokelvin. Atom number is of the order of 1,000 to 1,000,000 typically, although they can go larger. And so these are very dilute and therefore weakly interacting. And in a harmonic trap, because typical experiments are done under harmonic confinement caused by magnetic fields, basically you typically have, what you're seeing here is velocity distributions, which effectively show you how the atoms are partitioned in the trap before the trap is removed. And the typical case is that you actually have a situation somewhere below the critical temperature, but where the system is not a pure condensate and it has a broad thermal component around it. And the question is, what does the presence of the two actually do to them? And so that's what I'm going to be focusing on. So here's the familiar Gross-Pitevsky equation. You've heard a lot about it. Okay, it's basically an equation for a classical amplitude. So if you're thinking in terms of field theory, then it's the mean field of the Bose field operator. Okay, you can write it in a density phase representation, and you get an equation for this. You can think of this as the wave function for the condensate, if you like, this field phi. But there's two ways to think about it. One of them is the very simplistic way. Well, this is really a zero temperature case. It's just the lowest energy of the system. It's the condensate and nothing else. So you assume there's no thermal cloud. You can also use the same equation in a different context, which is used a lot in field theory, basically. You can think of it as an equation for a classical field. And then you can even start playing games by seeding it with random initial conditions, and then you actually get fluctuations into the system just from the seeding into this equation, and then you have a high finite temperature description as well. So the question is, can we go beyond these or generalize them in some form? Okay, so the first approach is still based on symmetry breaking, but what we're going to do is now assume that around this mean field, there's actually some fluctuations. And we'll just limit the treatment to basically this quantity here, so thermal fluctuations. No quantum fluctuation here, a straight case condensate plus thermal cloud. So this is nice and not so nice depending on your perspective. What is nice about it is that you actually get two systems. You get a condensate and you get a thermal cloud, and you get a system of two coupled equations that you can solve. It's like a two-fluid model, if you like. Of course, this is quite artificial. If you think about what an atom sees, an atom doesn't know about a condensate or a thermal cloud. Okay, an atom just sees the total distribution. The key thing here is that actually, because of interactions, the thermal cloud is sitting at the edge of the condensate. So what you see here, there's no vortex or anything. This is just a equilibrium distribution of the thermal cloud. Okay, so because they coexist, if we take the view that they're two separate things, each of them will move through the mean field of the other component, and so we expect some modification. So let's come to the question then that's of interest to many people here. How does a vortex evolve in this case? Okay, and here's actually a schematic of what the model includes, just to introduce this model basically. You have the condensate, that would be your sort of standard Gross-Pitevsky equation basically. Then if you think of just a purely thermal gas, you would have a Boltzmann equation with standard binary collisions. But of course, if you have these two systems coupled to each other, then you will have evolution that allows for atoms to go from one system to the other, and so on. Okay, so you have a system of two coupled equations. This is your generalized Gross-Pitevsky. Okay, these two terms here are the new terms. Otherwise, it's just the ordinary Gross-Pitevsky equation. And this n prime is basically the thermal cloud density, which you can study by looking at the quantum Boltzmann equation evolution. So the two equations are coupled, of course, by mean field coupling, because one sees the existence of the other. But there's other terms, and this is quite important. This is exchange of atoms between the two systems. These are these arrows here, this C12 IR. So two particles collide in the thermal cloud. One goes into the condensate, one stays in the thermal cloud, or vice versa. And of course, there's thermal-thermal collisions where everything happens in the above region there. So what about a single vortex then? Well, if you have a vortex, these are harmonically trapped systems. So at zero temperature, what you would expect is a circular trajectory at the equipotential line for the vortex. Okay? Because of the finite temperature and the relative motion through the thermal cloud, you're basically getting dissipation. The vortex is spiraling out with a gradually increasing rate, and then it decays eventually. Okay? So if you look at the condensate density, here's the vortex moving around, represented as a hole. If you think what the thermal cloud is doing, well, the thermal cloud is seeing a lower potential in the region of the vortex where there's no atoms because of the vortex from the condensate. So there's always a thermal cloud peak in the region as the vortex is moving around. Okay, so the thermal cloud is filling in the vortex core. If you do different temperatures, then what happens is, of course, it decays faster. And if you look at the vortex position, basically, as a function of time, then you can look at, you see basically exponential increase to quite good degree, at least initially, until it reaches the edge when it, this just changes a bit. And so we can study the temperature dependence of the decay, okay? And what you see is, of course, just focus on the black dots here, okay? Basically, the decay rate is, of course, increasing with temperature. You would expect that larger thermal cloud. What is shown here is the role of collisions. If you had a static thermal cloud, it would be all the way at the bottom, just this red stars here. So really, collisions play a very crucial role in the vortex decay. The intermediate lines I don't have time to go into, but show the dependence of which term does what. And what we find is that actually the crucial term is the collision between the condensate and the non-condensate that causes the decay, but thermal-thermal collisions further affect this evolution. Okay? And similarly for the change of frequency, and preliminary experiments indicate a similar picture. Okay? Now coming back to the idea of these equations for the evolution of the vortex. Okay, what we have here is, of course, the evolution that the vortex would have. I don't need to say too much because that was introduced earlier. Okay, at zero temperature, and then we have the finite temperature effects, this alpha and alpha prime coefficients. Okay, and the question was, can we parameterize and see what these coefficients are from our model? And what we find is a strong dependence of alpha on temperature. It increases rather rapidly as temperature is increasing in terms of the transition temperature. For alpha prime, we find basically something more or less consistent with zero. Okay, we cannot infer a zero thing. There are some large errors. We're not sure exactly what's happening at all those points, but we can certainly put upper bounds on alpha prime, and this is similar to other works that have been done, and that suggests that it's not a very crucial effect. Okay, we can start playing other games now. We have a condensate and a thermal cloud. We can set some rotation to the thermal cloud, and depending on this, we can slow down or accelerate the vortex decay, because basically, if you think about it, the vortex is rotating. If the thermal cloud is co-rotating, then there's less relative motion, which is the key issue for the decay. And so you can slow the vortex decay, or you can speed up the vortex decay. And it can be you can think of this as a sort of parametric driving. By driving the thermal cloud, you're parametrically driving the vortex in or out. Okay? If you now go for a vortex lattice, what you expect is, of course, that the vortices will decay compared to no decay in zero temperature evolution. And what you see here for quite a high temperature is the decay of the vortex lattice. Now, the evolution will depend critically on the geometry of the lattice. So it depends on whether you have a central vortex or not in the vortex lattice. And we find that when there is a central vortex, it lives along for very much longer time. There is, of course, a catch here. Even though that is a true picture, there is a catch. The model I've described has no mechanism of kicking really this vortex easily from the center stochastically. It can happen from the sound waves emitted from the other ones, but it tends to be very long-lived. What we really want is some sort of stochastic kick that basically sends the vortex jiggling about, and then that would lead to faster decay. So this brings me up to the other model, basically. So far, everything has been deterministic. We're just describing the average motion of a vortex at finite temperature. In a realistic system, you actually have fluctuations. Okay? That can happen, for example, if you're close to phase transition, or in low dimensions where fluctuations are really amplified. Okay? So then we need to consider an alternative model, which is based on microscopic considerations. For all practical purposes, you can think of it as, again, a Gross-Pitayevsky-like equation coupled to a thermal cloud, and then you have an associated stochastic kick, an associated noise, which is Gaussian here. Okay, so what does this new field phi here represent? Well, this is precisely this classical field. This represents the low-lying modes of the system that are affected by the condensate. Okay, and then you still have thermal modes above. So for simplicity, we tend to treat the thermal modes as a heat bath. So it's basically a classical field coupled to a heat bath of purely thermal modes. And of course, your total system density, if you do comparison to experiment, is the sum of those two densities. And it's quite crucial for cold atoms to really include this part to match to experiments. So the equation we actually solve is a bit simpler. So what we do is we take out this part IR that was here. We can rearrange, and it looks like a dissipative Gross-Pitayevsky equation, only this gamma is now obtained ab initio, but there's still a coupled noise term here, so the strength of the noise is of course related to the dissipation. And that's the equation that we really solve, which also has these stochastic kicks. And so what does a single run look like? If you solve a stochastic equation, you want to model the average. But what about a single run? And so you're going to see here the evolution, how the classical field grows from nothing, basically. And what you see is it grows, and as it grows spontaneously, you're seeing these vortices appear, and here you saw a vortex, anti-vortex, annihilate. So that's indication, there's no rotation here of spontaneous formation of vorticity. And this is the Kibble-Zurek mechanism, well known in high energy and also condensed matter systems. Here's a 3D and much more detailed representation rather than my toy simulation here done by the group of Matt Davis. And these are 3D simulations. There was actually an experiment that was done in cold atoms that, like in other condensed matter systems, has verified the idea that basically as you're quenching through the phase transition, vortices get frozen in because phase fluctuations get frozen in, and that is the Kibble-Zurek mechanism. So I also want to mention another thing you've heard earlier in the conference, the Brzezinski-Kosterlitz-Saulus transition when you're in two-dimensional system. Okay, this has been seen experimentally in cold atoms. Here, what I'm going to focus on is just to argue that you can actually see scale invariance and universality from an experiment that was done at the University of Chicago, actually. And so what you see here is at different temperatures, the densities and the density fluctuations. Red is the experiment, then there's various theoretical models. I don't want to go into detail. If you plot things, even though these are very different, if you plot things scale invariantly by scaling to the de Broglie wavelength, or basically this is the chemical potential locally because you have a harmonic potential trap, and beta is of course the inverse temperature. Okay, you can recover all the experimental results, which are the red, by using simulations of this stochastic model. So this shows basically you have the transition from a normal gas to a superfluid through the fluctuating region where the Kosterlitz-Saulus transition is taking place. And what you can do is you can do fits that are known basically for this universal parameter here. You can extract the critical chemical potential, map that onto your data to extract the critical temperature, and then you can plot everything in a universal thing which depends on the deviation of density from critical density, chemical potential from critical chemical potential on temperature. And that is now universal behavior because you can see that you can change the strength of interactions in the system, which can be done experimentally, and everything just falls on a curve. And this is in agreement with earlier simulations from Zvistinov about Monte Carlo predictions. Okay, so we can, in cold atoms, one-dimensional systems are also very interesting. Then of course you don't get vortices, you actually get solitons basically, so spontaneous soliton formation. And we've actually done a lot of work studying mapping on these one-dimensional experiments. With that, I've concluded my time completely. So I'd like to say that I hope I showed you about vortex decay in quantum gases. You can model that deterministically. Thermal motion is very important, the thermal cloud, but fluctuations also play a key role. You can get things like Kibble-Zurek mechanism and the Brzezinski-Kosterlitz-Saulus transition, and you can study that with this other stochastic model, and things are consistent with experiment. And I should mention the people that have done a lot of this work. So Joy Allen and Carlo Barenghi are in the audience. They were involved in the kinetic theory, so the first part of the talk. Then Stuart Coburn and Donatella Gallucci on the other thing. Eugene Zaremba also collaborated on the first part. I never had time to talk, and I apologize. Angela White has a very nice poster outside that I encourage you to go and see. And thank you very much for your attention.
Time for one question. computers are you using to do these calculations? How much memory?
Normal computers is not much at all, actually.
Okay.
It's,
Good.
In the Kosteler-Staros transition you see, is there a lot of difference in the transition that you see in this case versus, for example, that which you can see in colloids?
I'm not sure. You would expect the same universal scaling and things like that, but I'm not sure I could answer more because I don't know enough about what you see in colloids. But you can really see the appearance of the spontaneous vortex and things like that, not in what I've done, but in a single run. You just see basically vortex.
Yes, this was also seen in magnetic colloids.
And it's been seen in many different systems, yeah. And so the fundamental principles are always the same. I don't know about specific details, but
Okay. So,